So hello again. At this point, we are going to introduce the backordering concept into the lot sizing problem. And remember now, in this model, we are trying to optimize this problem. So in the end, we are trying to find the optimal lot sizing policy using either the integer programming model or the dynamic programming model. So we have done this already in the previous week. Now we are going to introduce the concept of backordering. So we say that in the end of any period, we can think about ending up with a negative level of inventory, which means we are promising our customers that we are going to deliver their products ultimately in the future periods. That means you are postponing the demand of the customer. Okay. So if you end up with a positive level of inventory in the end of a period, this means with these periods inventory, you can meet the demand of the future periods. Okay. Now, if you are allowed to end up with a negative level of inventory, this means the previous periods demand can be met by the future inventories. Okay, so basically you are getting in debt to your customers and you can end up with a debt. This is introduced to our problem as a negative inventory level in the end of a certain period. Now we have said that if you end up with a positive inventory in the end of a period, that inventory must be carried to the next period, and you need to pay a inventory carrying cost for each unit, which is denoted by HI, if you remember. Now here we are introducing the symbol PI, and that is the unit backordering cost from period I to period I plus 1. So if you end up with a negative inventory in the end of ith period, for each negative unit, you need to pay a unit backordering cost PI to carry this negative inventory to the next period. Okay. So PI is the unit backordering cost. And by assumption, my friends, for any period, PI value should be greater than HI value. Okay, because inventory backordering, unit backordering cost must always be greater than the unit carrying cost here. And this is actually a natural assumption. And W max is the maximum allowed backordering quantity at any period. So in order to simplify our solution, basically, we say that in the end of any period, you are only allowed to postpone up to a certain amount of demand. So you are saying that W max is the maximum allowed backordering quantity. So the absolute value of the ending inventory level can never exceed this. So if you end up with a negative inventory level, that negative inventory levels absolute value can never exceed this W max. So this is just for simplification. Actually, you can allow this W max to be infinity, which means, I mean, you can backorder the demand at any quantity that you want. That is possible, but I mean, your objective function is not going to let that happen. So in the objective function, if you backorder so much, you are just going to end up with a large cost, obviously. So this is introduced because we want to simplify our problem, the dynamic programming solution. We do not want to make this so complicated, because the number of calculations that you are supposed to do if you do not have such a limitation can increase so much. So this is for simplification purposes. Okay, so there is and by the way, I mean that can also be introduced as a policy by the inventory manager. So inventory manager says that yes, we are allowing back ordering, but up to a certain quantity. And that certain quantity is W max, which is the maximum absolute negative inventory that you may have in the end of any period I. Now, what happens to the integer programming model if we introduce this change? The first thing, that the decision variable xi, which is the ending inventory level of period I, now it's unrestricted, so it is free. It is not necessarily greater than or equal to 0. So in the previous model, if you remember, so let me show you the integer programming model here. So we were saying that in integer programming model, when the backordering was disallowed, So here, the ending inventory level of the ith period should be greater than or equal to 0 and integer. So that means there's a non-negativity restriction for the ending inventory levels, which does not allow you to adapt backordering policies. But here we say that when the backordering is allowed, this xi value can as well be negative as it can be positive. Okay. So now the ending inventory levels are unrestricted variables. Now, when you are developing a standard model for a linear programming model or an integer programming model, how do you solve this problem? How do you deal with unrestricted variables? Now, one way to deal with such a problem is to write the unrestricted variable as the difference of two non-negative decision variables. So we say that each ending inventory, xi, is going to be expressed as the difference between two non-negative decision variables, xi plus and xi minus. Okay. Now, by the way, such a modification to make this unrestricted decision variable equal to the difference of two non-negative decision variables is actually it has a physical meaning in this problem as well. So this is not just a dummy development. We are not introducing dummy decision variables here. These decision variables have physical meaning in this problem. So let's just say in the end of a period, you either end up with a positive amount of inventory or you may end up with a negative amount of inventory. So if you end up with a positive amount of inventory, that is represented by xi plus. That is the positive inventory level in the end of period I. So xi plus is equal to xi when xi is greater than or equal to 0. If the ending inventory level is greater than or equal to 0, then positive inventory level in the end of the period I is also equal to the same value. Now, xi minus, however, is the backordered amount in the end of period I. So if you end up with negative inventory level in the end of period I, that backordered demand amount in the end of that period is denoted by xi minus. Okay. Whenever the ending inventory level xi is less than 0, we say that xi minus is equal to the absolute value of that negative value. Okay. Therefore, the ending inventory level is expressed as the difference between the positive inventory level, if it exists, and the negative inventory level, again, if it exists. By the way, this negative inventory level's absolute value. This is the backordered amount. Okay. Now, please be careful here. In the end of any period, you either will have xi plus positive or xi minus positive, or maybe they are both going to be equal to 0. So in the end of a period, you may end up with 0 level of inventory as well. But two of them can never be greater than 0 simultaneously. So how this is going to be achieved? When you introduce both of these values in the objective function, obviously the minimization procedure is going to force one of them to be equal to 0, and the other one can either be 0 or positive in that case. Okay. Now, the inventory level process, which is described early in our last week's lecture, is going to be updated. So if you remember, let me show you the inventory level process. In last week, we have said that you start any periods with the initial inventory level, which is the ending inventory level of the previous period, which is xi minus 1. So you start with this initial inventory level, you manufacture QI units, or you order QI units to receive them in the same period again. And the demand in that period withdraws inventory from your withdraws products from your inventory, and that basically determines the ending inventory level of that period. Okay, so this is how we construct this equation. If you remember, the ending inventory level is the beginning inventory level plus the order quantity minus the demand in that period. Now we are going to update this inventory level process. Now, instead of introducing the inventory level of the previous ending inventory level of the previous period as a single component, we say that we have a positive inventory level in the end of the previous period and a negative inventory level in the previous period multiplied with -1, which means the backordered amount. Okay, so negative inventory level is negative. But when you multiply it with -1, it becomes the backordered amount, okay, the backordered quantity. So you end up with a positive, either positive inventory level in the previous period or a positive backordered amount in the end of the previous period. Now, the summation of these two values is equal to the ending inventory level, which is either positive or negative. It depends whether this or the second one is positive. Now, the ending inventory level of the previous period plus the order quantity minus the demand of the period, that determines the ending inventory level of the ith period, as you can see. So we say that the ith period ending inventory level, which is expressed as the summation of the positive inventory level and the backordered amount, as you can see, is equal to the ending inventory level of the previous period plus the order quantity here minus the demand. Now, please remind yourselves about this. Again, the decision variables in this equation are basically everything except the demands. So we are collecting every decision variable on the left-hand side of the equation, and the I will remain on the right-hand side when you are introducing these in the mathematical model here. Okay. So you need to be very careful about this. And also, when we are going to develop the forward recursive equation for the dynamic programming model, for this model, we need to relate the ending inventory level of the previous period to the ending inventory level of the next period. So in the forward recursive equation, we need to understand this relationship. So when we say the ending inventory level of the ith period is dependent on the ending inventory level of the previous period and the order quantity and the demand of this period. Now, when you collect every decision variable on the right-hand side except the ending inventory levels on the left-hand side, then we say that the ending inventory level of the previous period is equal to the ending inventory level of this period minus the order quantity plus the demand of this period. So this relationship is necessary to understand to construct the forward recursive equation for the dynamic programming model of this problem when backordering is allowed. Now, the only thing that you need to understand as a difference between the above equation and the below equation here, the above equation calculates the ending inventory levels in the direction of time flow, but the second equation here calculates the ending inventory levels in the reverse direction of time. But that is necessary to construct a forward recursive equation. Okay. Now let's update our integer programming model in the beginning. Then we are going to focus on the dynamic programming model. So we say the objective function this time consists of 4 components. The first component is the ordering cost, obviously. If we release an order in period I, then the decision variable yi is going to be equal to 1, which will introduce the fixed ordering cost associated with that period as ki. Now, when you allow yi to be equal to 1, this means you can release a positive order quantity to your supplier, and for each unit you need to pay a CI dollars of unit purchase cost. So from a period, first period to the last period, the total of this variable purchase cost will give you the total variable cost. Finally, you may end up with a positive inventory level or a negative inventory level. Now, if you end up with a positive inventory level, then xi plus will be positive. So for each unit, each positive inventory level in the end of period I, in order to carry each unit from this period to the next period, you need to pay a carrying cost, unit carrying cost of hi. So in the end of the I period, xi plus must be multiplied with hi. Now, xi plus can also be equal to 0. So in that case, you do not pay any inventory carrying costs. For example, if there's a back ordering in the end of this period, you do not pay any inventory carrying cost. And finally, obviously the summation of these inventory carrying costs from the first period to the last period will give you the total inventory carrying cost. And finally, if you have a backordered amount or backordered quantity in the end of the ith period, which means xi minus this decision variable is going to be positive. If you backorder a single unit from the ith period to the I plus first period, then you need to pay a unit backordering cost or the penalty cost as PI. Now, when you multiply this unit penalty costs with the total amount of backordered units in the end of the ith period, you will be calculating the backordering cost associated with that period. And when you sum these up across the periods, you will be calculating the total backordering cost. As you can see, each component is expressed as a summation over the periods. Therefore, when you combine all of them in a single summation, for each period, you are basically calculating 4 cost components: KI, YI, CI, QI, HI, XI plus, and PI, XI minus. Okay. Now, this objective function, I mean, when we have not introduced the constraints, or we have not updated anything in the constraint set yet, but when you look at this objective function, you will see that this objective function will not decide both xi plus and xi minus to be positive. Okay, so if it is going to minimize the objective function in the end of a period, you either will end up with a positive amount of inventory, or you are going to end up with a positive backordering amount, or you are just going to end up with 0 value for both of these decision variables. Okay, but they cannot be positive simultaneously for a single period. So let's deal with the constraints. How do we update the constraints? First of all, again, we have the capacity constraint, or the maximum ordering quantity in any period. We say that the order quantity in any period can never exceed the Q max value. This is the maximum order size that you can define in any period. And again, the maximum backordering size in the end of any period can never exceed W max. So we say that the ending inventory level in the end of any period, which is the backordering amount in the end of any period, xi minus, these values can never exceed the maximum allowed backordering size in the end of a period. Now, the third set of constraint is introducing the dependence between the binary decision variable yi, which is associated with the initiation of a production run or releasing an order. So if yi is equal to 0, then this constraint forces qi to be equal to 0, which means if you do not release an order, you can not receive any positive quantity. If yi is equal to 1, however, then qi is just going to be any non-negative value as long as it satisfies the first set of constraints, obviously. So this relationship is basically creating the dependence between yi and qi values. Finally, we have the fourth set of constraints here, which is the balance constraints here. So previously, we have defined this constraint as qi plus xi minus 1. I'm sorry, let me show that to you. That's just going to be better. This is how we constructed qi plus xi minus 1 and minus xi is equal to di. So this is basically creating a dependence between the ending inventory levels of consecutive periods. Now, the ending inventory levels of consecutive periods this time is expressed as the difference of two non-negative decision variables, if you remember. So let me explain this in the as long as it is possible. Okay. So this means the production quantity or the order quantity in the ith period plus the ending positive inventory level in the previous period minus the ending inventory level of this period, positive inventory level of this period, minus the ending backordered amount in the end of the previous period plus the ending backordering amount in this period. This summation should be equal to the demand of this period. Okay. The only difference between the previous constraint is what? The xi minus 1 value here and the xi value here are expressed as the difference of the two non-negative decision variables, which are associated with the positive inventory level in the end of the ith period and the negative inventory level in the end of the ith period. Now, the initial inventory level is a parameter introduced to this problem, so you can never change the initial inventory level. It's not a decision variable. So we say that x0 plus minus x0 minus should be equal to the initial inventory level, and xn plus minus xn minus should be equal to the ending inventory level. Again, the ending inventory level is an objective that you need to satisfy. You can say that we intend to end with 0 level of inventory in the end of the planning horizon. That is your choice, but I mean, sometimes the inventory managers would like to get prepared for the next planning horizon by defining a certain amount of buffer inventory in the end of the planning horizon. So that will make the ending inventory level xn a positive value, but again, we need to introduce xn plus and xn minus values as decision variables. So we need to express these two values if we are going to write the fourth set of constraints here. For each I value here, we need to express that these values must be equal to x0 and xn. Okay. Now, the binary decision variable yi is binary. It is introduced by this binary constraint, and both the order quantities and the ending inventory level must be integers and greater than or equal to 0. And the backordering amounts in the end of any period, they must also be greater than or equal to 0 and integer. So this is the overall integer programming model that we have developed. Okay. Now, obviously, we can solve this problem using Excel. Just by introducing these decision variables. This is the only change that we have to do. And by the way, you may ask this question: was it possible, instead of introducing this ending inventory level this decision variable as the summation of or difference of two non-negative decision variables, instead of this method, can we leave it as it is like this? Now, unfortunately, not, my friends, because I mean, this is a typical situation in the unrestricted variables, in the case where we have unrestricted variables in mathematical models. So definitely, you need to update your model from this state to that state if you allow the backordering. Okay. If you just say the ending inventory levels are unrestricted, okay, if you just would like to keep xi values as xi's instead of expressing them as the difference of two non-negative decision variables, then you cannot introduce the unit backordering cost separately from the unit holding cost. Okay, so because I mean they are different, right? So this is a necessary change that we need to introduce in our integer programming model. So I'm going to explain the updates in the backordering case in the optimal load sizing problem, if we intend to solve it with the dynamic programming approach, obviously. In the next video, we are going to discuss about this.